This time I'll be talking about debugging and understanding natural language processing models. And this is a very big research topic recently, very important. And so let's get started. So if we think about a typical situation in developing models that you're using for whatever task you're interested in, you've implemented an NLP system, maybe usually based on a neural network style model, like all the ones we're doing in class. You've looked at the code and it looks basically okay. However, it has low accuracy or it makes incomprehensible errors. And because of this, you kind of like to know, why is this going on? What is the problem with my model? So what do you do? In order to figure this out, there's a bunch of tools that you can have in your toolbox. And specifically debugging methods that basically identify problems in your implementation or assumptions. And by debugging, I mean more like kind of code level debugging as opposed to like data debugging or other things like this, which are kind of popular recently. Another thing is interpretable evaluation. And so this is identifying typical error cases of an implemented system on a finer grained level than just, looking at individual evaluation metrics. And then another thing is interpreting predictions, examining individual predictions to dig deeper for why those individual predictions happened. And there's several methods for each of these different things. I'm going to kind of go from top to bottom here. And the reason why is because I would recommend that you start with the things on the top and move towards the things on the bottom as you try to figure out what's going on with your systems. Okay, so first about debugging. In neural network models, debugging is really important, and it's also relatively hard because the models are kind of black boxy, or unless you can, do matrix multiplies in your head, you can't really tell what's going on, right? So models are often complicated and opaque. Another big problem is everything is a hyperparameter, including network size, model variations, batch sizing or strategy, optimizer learning rate, et cetera, et cetera. And sure, as you gain more experience, you'll kind of gain an intuition about these particular things, but until you gain that intuition, it's relatively difficult to figure things out. Another thing is you're doing non-convex stochastic optimization. So a neural network, unlike some other methods, like a linear regression or logistic regression, they basically have a loss surface that looks like this. Or actually, this would be that wouldn't be a loss surface. Your loss surface would be going down. So linear regression, logistic regression, support vector machines, they have a loss surface that looks like this. So you can be guaranteed that if you're descending the loss surface, you're eventually going to arrive at a good solution. However, for neural networks, that's not the case. They have a loss surface that looks like this. That's full of, local optima. And because of this, you have no guarantee that, you're going to be decreasing loss overall. And what makes it worse is you're doing something like stochastic gradient descent, where you don't process the whole data set at a time, only a little bit at a time. So basically, neural networks are hard. And so my recommendation for how you can do debugging, which is very, I think, useful overall, is you need to break down why the problem is happening, like what problem you're why the problem you're encountering is happening. And this can include training time problems, which can include lack of model capacity, a poor training algorithm, a training time bug. You can also have test time problems, which include a disconnect between what you're doing at training time and what you're doing at test time. Failure of search algorithms if you're doing some sort of search. Another problem is overfitting. And another issue is mismatch between the function you're optimizing and how you're evaluating your model. And all of these things are things that you will encounter if you are training NLP models for a long time. The important thing is to identify which one of them is the problem you're actually encountering, because then that allows you to quickly debug it and fix it. Another thing is the ones at the top tend to be like easier to diagnose than the ones at the bottom. So it's a good idea to start with the ones at the top and work your way down. Okay, so let's look at debugging at training time. So the way to identify training time problems, or my recommendation for identifying training time problems, is to look basically at the loss function on the training set. And this is not what we're going to be doing eventually. Eventually, we're going to be looking at the evaluation function on the test set. So in order to do this, you need to move out of the mindset of like optimizing your accuracy or optimizing your blue score and focus on the training time problems. Says, sorry, I had a question. Do I have slides for the lecture? It looks like I'm screen sharing. Can people see my slides on Zoom? Oh, the previous version. Oh, I'm sorry. I will upload these. There's not a huge difference between the previous version and the current version.
The slides is from the
Oh, I see. Okay, let me. Sorry about that. Okay, so here are the ones from last year. The ones from this year are, I shared it on Zoom. If you click on any slide, if you're in the class but not on Zoom, you can click on any slide. And I believe that should be there for so these are definitely the ones from last year. The ones from this year might be uploaded also, so you can click through the link. But I'll fix this afterwards. Anyway, the ones from last year should work too. Okay. So in order to identify training time problems, if you look at the loss function calculated on the training set, what you'll want to be looking at is whether the loss function is going down on the training set. Also, is it going down basically to 0 if you run training for long enough, especially on a smaller data set? So if your loss function is not going down to 0, you certainly, on a data set, you're not being able to overfit the data. And that indicates that you have a problem. What could the problems be? One problem could be that your model is too weak to solve the task. This is particularly the case if it's maybe overfitting on a small data set, but not overfitting on a large data set. And one very salient trait of NLP nowadays is that larger models tend to perform quite a bit better, even with respect to generalization. But especially with respect to memorizing the training data. So if you're not able to memorize the training data, maybe your model just needs to be bigger. Another interesting thing is that larger models can learn with fewer steps. So this is a very nice paper, and a lot of people have been kind of examining why this happens. But just to explain what is happening in this figure, on the left side, we see the number of tokens processed. On the y-axis, we see the test loss. This could also be similarly the training loss. You'll see similar trends for the training loss, but this is the test loss. And this is tokens processed, and this is the amount of compute. And then the darker colors represent a smaller model. The lighter colors represent a larger model. And what you can see is that if you process the same number of tokens, the larger models almost always converge faster. If you consider the amount of time, because processing a certain number of tokens with a large model takes more time than processing the same number of tokens with a small model, you can see that at some point, at the very beginning, the smaller models are faster to train, but at some point, basically the smaller models level off and the larger models surpass them in how good the models are, even at the same amount of training time. So this is very interesting. It's basically like, training a bigger model allows you to learn better, and it even can allow you to learn faster. Why is this? I don't have the reference on the slide, but there's a nice paper called the lottery ticket hypothesis. Which kind of explains this. Another way you can think about it is, if we look at the simple XOR function, like this, this is a simple function, and you only need a feed-forward neural network with two nodes to learn this function. Basically, you can learn one function to identify things on the left of this line, another function to identify things on the right of this line and on the left of this line, and then if either of them is true, you can learn that. So a two hidden node neural network can learn this. However, if you actually try to train a two hidden node neural network, it only learns this function correctly about 30% of the time or 40% of the time, or something like this. And the reason why is basically because it's if the model is not initialized properly, it will fall into a local minimum where it just learns kind of the linear classifier that gets non-perfect accuracy. However, if you learn a 50 hidden node neural network, it will learn this perfectly every single time. It will always be able to solve the XOR function. And the reason why is because within your 50 hidden nodes, there's probably, even without any training, there's probably at least, one line that is learning the appropriate features. You have 50 of these lines, right? And because of that, basically by initializing a whole bunch of these features, you get lucky at the very beginning, and some of them tend to be useful. Some of them are not useful, and then they just disappear during training. And that's what this lottery ticket hypothesis is saying. It's saying that if you initialize a whole bunch of features, some of them tend to be helpful, and those are the ones that kind of ensure that the model is able to work well. So if you have a really big model, you just have more chances to, have a good initialization that can learn the features that you need to learn. So that's my general hypothesis. I think there's a lot of support for this in the literature, but that can help explain that. Any questions about that or discussion? Yeah.
Maybe like in the nodes, talking about parameters. So in that stage, maybe the loss function is a bit more like the local numbers aren't too bad. Lower products in the number. So can that be a reason for this to happen?
Yeah. So just to repeat the comment, maybe when there's more parameters, the optimization surface will not look quite as peaky like that. And I think actually those are two ways of saying the same thing, perhaps. But yeah, I think you can also look at it from the point of view of the learning dynamics or the loss literature as well. Cool. But anyway, long story short, larger models tend to learn better in fewer steps. It's an important thing, and they converge to better places in the end. Okay. So another problem is trouble with optimization. So if increasing the model size doesn't help, you may have an optimization problem. So you might have a problem where you'll want to check your optimizer, your learning rate, your initialization. Also, mini batching, are you using sufficiently large batches? You'll want to pay attention to all of these details when replicating previous work. Nowadays, most of NLP has kind of consolidated around using Atom, but with a decaying learning rate at the end of training. So I think that's a good standard to be using. However, it's very common to see learning curves, especially when training larger models, that go down like this and just like spike, or things like this, because the model gets into kind of a bad state where some of the weights are very, very high and it kind of diverges. If you're encountering a problem like this, you might have a bug in your code, or you might just need to adjust the learning rate, restart training from where you started off, so it doesn't with a different random seed for your data shuffling or something like this. So this is kind of a thing that you need to worry about. For smaller size models, it's maybe not as much of a problem. Another standard thing is mini batches. Basically, larger tends to be more stable. So if you're using very small mini batches, then that can also cause your model to diverge more easily. So these are good implementation details. These are kind of training issues. You can debug all of them by looking at the training loss function. Another thing is debugging at test time. And at test time, one of the big issues is if you have a training time test time disconnect. This isn't so much a problem for something like, usually it won't be a huge problem for something like text classification or something like this. It's more of a problem often for things like sequence models or other things like this. And very often, your loss calculation and prediction will be implemented in different functions. And because of this, duplicated code is a source of bugs. So you can run into a case where like you're training a model and it's training well, but when you're decoding or when you're generating outputs, you might be generating outputs that don't actually match what you were training for. Another issue is that loss calculation can be mini batched. In generation, very often you just have a mini batch size of 1. So there are some really good tricks that make it easy to debug this if you need to implement it yourself. And so debugging mini batch loss calculation, a very easy way to do this is calculate the loss with a large batch size, then calculate the loss for each sentence individually and sum all of them together, or calculate mini batch size of 2 and do that 16 times. And the values should basically be the same. However, if you have a problem in how you implemented batching or something like that, it's very often that these values will not match. But luckily, this is very easy to debug. Like it's an obvious problem, so obvious problems are easier to fix. You can also create unit tests that test this. Another problem is structured generation, like generation from a like machine translation or sequence model. And your generation code should basically get the same score as the loss calculation is one thing that you should pay attention to. So one way you can test this is you can call the generation function. So whatever function you're using to generate outputs, you can generate the output. And almost always this will also keep track of the score, right? Because you calculate the score when you're generating the outputs. Then after that, you can put this through your loss function, calculate the score of your loss function, and these should match, right? Because the score calculated when you're generating should match the score that you get when you're calculating your loss. And if they don't, that is indicative of an issue. And you can create a unit test doing this as well. I have had this problem countless times. Like, I think every time I implement some sort of generation function, I run into this issue at some point. So this is a very high importance thing if you're implementing it yourself. Beam search, this is a little bit more tricky. We talked about it before, but one thing you can do is as you make search better, the model score should get better almost all of the time. And so what you can do is you can search with varying beam sizes. You can increase your beam size and make sure that when you increase your beam size, you get a better overall model score with larger beam sizes. And so basically, you know, you do decoding with beam size of 1, you do beam size 3, 5, 10, and your score should be going from like, your log probability should be going from like -10 to -9.5, -9.3, -9.2, or something like this. And if it's not getting better, then that's indicative of an issue. So all of these are like kind of code level things, like your code is messed up. And code is messed up or your model size is not large enough, other things like this. Oh, sorry, I realized I had a question from 3 minutes ago. Given some fixed compute capacity, how do we decide on the trade-off between larger batch sizes and larger models? That's actually a really good question. I don't know if there's a clear-cut answer to that, because the effect of a larger batch size on training is unpredictable. I mean, you can kind of predict it, but it really depends a lot on, you know, all the other parameters. So I don't have a good answer for that. If somebody has a good answer, I'd love to hear it. I see another question. How do companies like Google, Microsoft, OpenAI conduct hyperparameter optimization debug all these things before the final training for large scale and expensive models like GPT or DALL-E? Do they use some math, or do they use empirical testing on smaller models? That's a very, very good question. I don't think it's math. So they certainly are doing testing of their code to make sure it works. Like, I think, you know, big corporations tend to be much better at testing their code than independent researchers do. So I can guarantee that. I think training smaller models and then scaling up is definitely something that people do. In fact, like, you can see that all of the models that the big corporations are releasing also have smaller counterparts. Like, there's GPT-3 with smaller versions and larger versions. There's also, you know, OPT and Bloom and other things like that all have small versions as well. So I'm sure that's something they're doing. I also strongly recommend that you do that too. Don't just start out with the biggest model because you think it will do well. Like, start out with a small one. It's way faster to iterate. So do that. Doing that as well is good. With respect to hyperparameter optimization, that's a good question. I don't actually know the answer for that as well, but I think hyperparameters get less important as your model gets larger. And because hyperparameters get less important as your model gets larger, probably tuning them once on a small model and then scaling up is reasonable, but there might be some changes there. Yeah.
One thing they do in general is they'll often release something on a very, very small scale and make sure it doesn't do crazy stuff. But like they've got millions of users, and so, like, you know, a couple hundred people will like get some test version or something.
Oh yeah, and at deployment time, yes, it's very common to release something on a smaller scale to make sure it doesn't do something terrible. Also, you know, making sure that you're not seeing horrible like bugs in their generation code or something like that as well. So I had another question on Zoom, which is larger model sizes, models should be better as they get better results. Larger batch sizes just make it faster to train, right? It's not actually necessarily the case that larger batch sizes just make it faster to train. It also makes it more stable. in training, because if you're using small batch sizes, you get a very noisy estimator of the gradient. And if you get larger batch sizes, you get a more stable estimator of the gradient. So larger batch sizes also help final accuracy as well. Okay, I'm going to move on to the next thing, the mismatch between the optimized function and the evaluation metric. This is something that I think people are maybe a little bit less familiar with, but it's very important. It's especially important in things like text generation. So if we think about our loss function and our evaluation metrics, it's very common, or almost like most of the time, we optimize for maximum likelihood during training. And however, even though likelihood is getting better, accuracy can get worse. So how common is this, or how easy is it to reproduce this problem? To do this, I trained a simple feed-forward neural network on MNIST, which is like a extremely simple like digit classification data set. And if we look at the loss and the accuracy, if we look at the test loss and the accuracy, we can see the training loss is converging. So like, as I said, it's going down and down. So that's an indicator that I'm training the model well. However, the development loss is diverging like this. And if you look, the accuracy on test is going up, on train is going up. On test, it's also going up. So our loss function is getting worse, but our accuracy is continuing to get better. So, oops, well, I was going to do a quiz about this, but I accidentally gave away the answer. So the reason why this happens is because the model gets more and more confident about its mistakes. And so just to give an example, let's say we have training and we have a true value of 1 and 0. So like the label for the first one is 1, the label for the second one is 0. And then we have the probability of 1 through training. And we start out with like, I don't know, 0.5, 1, 0.52, or something like this. And this example is slightly harder. The bottom example is slightly harder to learn than the others. So this one, very quickly, we start learning 5.9. Oh, sorry, I need one more example. Let's say this one is 0 also. So we start out, the model thinks like everything is positive. The top two, the model is able to learn. It's able to learn to get it right. The bottom one, for some reason, the model is like quite poor at learning this. And instead, it starts learning the wrong answer. And so like, or something like this. So basically, if we look here, and this is like epoch 1, 2, 3, 4. So if we look here, this is the first time this one became 0. So up until that point, basically the accuracy was 33% because it was getting the top one right and the bottom two wrong. And so at this point, we have like the slower learning one. We have the slower learning one improved the accuracy by switching from like the label of 1 to 0. But the bottom one, this is like a noisy example or something like this. And this becomes very, 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 very like wrong. The confidence of it being wrong becomes very, very high. And because of that, this is reflected in the loss a lot, right? Like a very, very confidently wrong example will get a very bad loss value. But the accuracy, in the accuracy, it's only like one example that's wrong. So if you have any sort of noisy data or some data that's harder to learn than others, you can start getting a really bad loss value on these like harder to learn examples, while the accuracy is still increasing or like kind of being flat here. And there's a concept of model calibration. I'm not going to go into it a whole lot, but model calibration is basically how confident your model, how well your model confidence aligns with your model predictions. And basically, if you have a poorly calibrated model, then your loss could be bad, but your accuracy could still be reasonably good. Are there any questions here? Yeah. I think so, but this happens because every model we have is so over-parameterized. This ends up being a problem regardless of the networks we're training. Yeah. You might be able to prevent it on MNIST, but practically no regularization for neural networks works well enough to completely prevent everything like that. One thing that does work is explicitly enforcing calibration, trying to explicitly enforce model calibration, and that might help solve that problem. I had another question. So you would imagine the gradient would push a wrong answer to the right direction. Would that not happen because the KL divergence is averaged over the batch or something else? Oh, so sorry, just to clarify, this would be happening more on the test set than it would be happening on the training set. So you wouldn't be getting any gradients on the on these examples because they're in the test set. And in fact, you can see that the loss and the accuracy are getting better on the training set. This like divergence is mostly happening on the test set. Okay, so basically this is a problem. It happens all the time. And in order to solve this problem, one principled way of doing this, in particular in the case of like structured prediction models, like sequence models or other things like this, there are ways to explicitly train your model to optimize like the error metric instead of or your accuracy instead of your maximum likelihood. These are just a few examples of them. But a much simpler method that we use a lot of the time is trying to do early stopping. And what early stopping does is it stops training before you're finished, but you explicitly early stop when your model gets the best accuracy as opposed to when it gets the best loss. And this largely solves the problem. This is also another form of regularization, right? Because early stopping is a form of regularization. So that's one example. So I'll talk more about these other methods here, but it's an important thing to know. Okay. So the next thing that I'd like to talk about is more interpretable evaluation metrics. So a first step towards understanding the outputs of your model better is to look at the data, specifically look at the predictions of your model. And I mean, like in some cases, this should go without saying, but in other cases, it can be hard. So let's talk about the easy case, where we can look at our model outputs. And this is for a task that we have strong intuition about. We're focusing on only one task, and it's in a language that we understand. So this is an example that I've seen tens of times since I started doing research on neural language generation models. You're missing the first word in your sentence. Like you have an off by one error in your generation. Your blue score or whatever evaluation metric you're using is like 2 points worse than the baseline. So like 1 or 2 points worse than the baseline could be for so many different reasons. But if you look at the outputs and just see that you're missing the first word of every sentence, it becomes pretty obvious that that's where your problem is. Another thing that you can do is you can look more systematically. And you want to look at like where your model is consistently failing. And like, for example, if it's consistently failing on named entities, you need a better model of named entities probably, and then you can focus on that. So one way to do this is just by looking at lots of examples, but I like to do this in a slightly more systematic way. And specifically what I do is I look at 100 or 200 error cases. Maybe these are cases where your model got it wrong. Maybe these are cases where your like generation score was relatively low. And you can try to group them into a typology of the different types of like sentences they are or other things like this. There's one example by this paper that's cited in the references that comes up with a typology of machine translation errors. And they take all errors, they sort them into like missing words, word order, incorrect words, unknown words, punctuation. And then they further break them down into all these different varieties. So like if you were analyzing a machine translation model, you could use this typology, which is pre-specified for you. But actually, I kind of encourage you not to do this. What I would suggest is rather just basically try to make these categories on the fly as you're looking at the outputs, because you never know what you're going to find. Like, for example, you might find an example where the input is so like, the input is just like garbage. It's like randomly pulled out, you know, characters or something like that. And there's no reasonable way where your machine translation system can do well on those. And I don't think that's included anywhere in this typology, right? So there's an idea, there's something called card sorting, I think that's the name. And the name comes from where you basically like you print out a whole bunch of things on cards and then you just group them into like groups together. And that's basically what I do. I go through all of the examples and try to sort them into like consistent groups. And then once I know that there's a problem on a consistent group, I go in and fix it. And this was actually my secret to building really strong machine translation systems when I was like working on creating Japanese English translation systems. Just find the biggest problem with the model, go in, come up with a method to fix it, go back and do this process again, find the biggest problem with the model, go in and create a method to fix it. And it's a way to do this very efficiently. Another thing is quantitative analysis. So you'll want to measure gains quantitatively. What is the phenomenon that you chose to focus on? Is that phenomenon getting better? And so this is like closely linked together with what method you're proposing, or you know, if you're comparing two models, and intuitively one model should be better for like a particular phenomenon, you can go in and explicitly measure whether that got better. So like, let's say you focused on a method that should be good for handling low frequency words. You can check whether accuracy on low frequency words is increasing. You focused on syntax, is syntax or word ordering getting better? You focused on search, how many search errors are being reduced? So basically, break down beyond just the accuracy and come up with these metrics. People submitted to Explain a Board and probably looked at it. This is an implementation of like these principles within software. But you can also do it yourself without having any particular software to do it as well. Just to give an example, like you have accuracy by text length and tokens. So you can look and see that one model is better at longer sequences or shorter sequences, or one model is better at one particular type of tag or another particular type of tag. And this is precisely what I'm talking about. So you come up with like some sort of subcategorization of the examples and see whether you're doing better or worse on them. Okay, any questions about these processes? Okay. I see, is card sort another name for bucket sort? It may be, but I don't think it means the same thing here. It's a good question. Okay, interpretation of predictions in model internals. So why do we want to interpret model predictions? There's a bunch of different reasons why we want to interpret model predictions. We might want to know, for example, like let's say we're training a text classifier that's trying to sort resumes based on whether the person should be given an interview or not at a company. Whether you should be doing this at all is a good question, but like let's say you were doing something like this. You want to be pretty sure that your model is doing it correctly or doing it for the right reasons. And in fact, if it's doing it for bad reasons, it might even be illegal, right? If it's discriminating based on gender or race or something like that, that could, be a very serious problem with legal consequences, moral consequences as well. Another thing is if you want to identify whether your model has actually legitimately learned a difficult pattern or is focusing on spurious correlations. The most famous example of this that people probably have heard of before, it's not actually a real example, but it's a pretty interesting example nonetheless, is there was a famous story about somebody who trained an image classifier to classify whether tanks were in a forest, whether a forest had a tank in it or did not have a tank in it. And supposedly all of the pictures of tanks were taken on a sunny day and all the pictures of non-tanks were taken on a cloudy day. So they trained this very, effective tank classifier that was actually a color of the sky classifier. And so it'd be nice to know before you deploy that in the field and try to classify tanks, for example. Another thing is kind of like from a scientific perspective, you might want to know what information a pre-trained model has captured internally. So that might be another reason. Sorry, I see two questions about in Zoom also. So I had one question about what does interpretable evaluation look like for text generation? That's a very good question. There's a couple things that you can do. You can actually like look at what this the site does in Explain a Board, but like instead of having an accuracy, you might just want to have like an evaluation score, like a blue score or something like this, in which case you can bucket input examples by length and say, what's the blue score by input length? Another thing that you could do is you could kind of subdivide each example and say, what is the accuracy on each individual word? So like certain words like named entities or other things like that have a higher likelihood of being generated appropriately by a model. So these are just some examples of things you could do. Another question is another famous example for spurious correlations, SNLI hypothesis only baselines. So to give some context on this, natural language inference is basically a problem that I talked about very briefly in class, but to refresh your memory, it's like there is a big dog, and like there is a dog becomes entailment, entailed, there is not a dog, not a dog, is contradicted. And like there are two dogs is neutral because there could be a big dog and a small dog, so you can't tell whether the third one is correct or not. So you basically put two things into a classifier and try to categorize entailment, contradiction, or neutral. But the problem is they created a data set through crowdsourcing, and essentially, if you had the word not in here, it was very likely to be entailment, because that's the easiest way, very likely to be contradiction, sorry, because that's the easiest way to come up with a contradicted sentence, right? So, oh yeah, there we go. And so basically, what you're trying to be solving the problem of telling whether these two sentences match together. But in fact, it's basically just looking at the output. Another thing is, like, I forget, maybe neutral sentences tended to be longer or something like that, just because of an artifact of how the data set was created. So that's another famous example. Okay, going back to interpretation. So, yeah. Get rid of the. Okay, so spurious correlations can manifest themselves in so many different ways that I don't think there's a general purpose way to get rid of spurious correlations entirely. Like, in fact, if there was, you've solved machine learning, basically. Because the whole point of machine learning is to identify real correlations, or the main point of like standard supervised machine learning is to identify, actual correlations and remove spurious correlations. So I don't think there's a general purpose way. There are some ways that you can try to mitigate it. Like, one example is through data creation, where you try to make like minimal changes and learn from minimal changes, or other things like this. But there's no general purpose way. So anyway, there's a lot of different ways to do interpretation. The most common way to do interpretation is something called the saliency map. And the saliency map is basically pointing out which inputs, is pointing out which parts of the input are the parts that we think the model is focusing on. And sometimes maybe in what way, whether we're doing it in a positive way or a negative way. A famous first attempt at this is something called LIME. And basically the way LIME works is if we have, let's say this is a spam classifier, and we have an input for Christmas song, visit my channel, like wink. And we need to make a prediction about whether this is going to be true or not. And so what we do is we take for a Christmas song, visit my channel, and we perturb some part of this vector. So in this case, we start out with like the one hot vector, including all of these words, and we perturb like three examples to be, 3 words to be 0, 2 words to be 0, 2 words to be 0, 1 or 3 words to be 0. We then add a weight to each of the examples based on how much we've perturbed them. And so the idea is we want to find examples that are close to the example that we're trying to interpret, the prediction that we're trying to interpret. So by weighting the ones that are closer together, we're basically upweighting the things that are close to this output. And then we have a probability here. And this probability is what the original model, essentially what the original model predicted with respect to these. Then given this, we treat this as training data. And using this training data, we train a interpretable predictor, like a linear classifier, to try to essentially fit this function. So what this is telling us is, if we train another model to mimic the model that we know we have, especially in the local area of a particular example, that might be a good explanation of why the model made that decision. And basically, if we train this model for this particular instance, channel gets a very high weight because it's kind of like the decisive, it's the decisive difference between the low probability and the high probability examples. And so basically what this is saying is channel is probably the thing that made the difference. Channel being included is probably the thing that made the difference and caused the original model to say this was a spam sentence. And this is a nice software package. It gives you some nice visualizations that say, like, I think this is a positive feature, this is a negative feature. I could maybe even show them. So basically it does things like highlight individual words and give you, like, the prediction probabilities are 0.58 and 0.42. But if you perturb these words, these are the things that would have reduced the probability. So these are probably the things that, I believe these are probably the things that caused it to believe that it was about atheism. These are the things that caused it to believe it was about atheism as opposed to about Christianity. And speaking of spurious correlations, like NTP posting host probably doesn't mean a whole lot about atheism. However, maybe .edu does. So if you have a .edu mailing address, you're more likely to talk about atheism than Christianity. And it's kind of like interesting to see that about the model, right? Okay. Yeah, any questions about that? Okay, so this is one example. These are perturbation-based methods. There's also a simpler version, which is like called erasure-based methods, where you just like erase individual things and try to see if that flips a prediction. But they're all based on the same general idea. Another thing is gradient-based scores. I'm not going to go into all the details of the math here for all of these. I think the most important one is maybe gradient times input or gradient norm. And basically what this tells you is you try to calculate the gradient. Like let's say we're talking about word embeddings rather than like this graph on the right. So what we would do is we would have all of our word embeddings. And then in addition to the word embeddings, we'd also calculate the gradient of the word embeddings with respect to the loss function, or with respect to the prediction. And based on this, we now have a gradient, and we have the actual value of the input. And there's a couple things we can do here. One thing that we can do is we can take the norm of the gradient. So basically what we're saying is if the gradient is larger, then it's more likely that this had an effect on the output. Another thing we can do is the gradient times the input. So basically we take the dot product between the two, which is saying that essentially, like, given that we have the input, how much is that affecting the output? Like if we doubled the magnitude of the input, how much more likely would that make the output? If we set the output to 0, how much less likely would that make the output? So another way to think about it is basically the gradient is saying if we make an infinitesimal step in the direction of increasing or decreasing the size of the input, how much would that make an effect on the actual output? Whereas the perturbation or erasure-based methods are not making an infinitesimal step. They're making a very big step of setting it all the way to 0. So it's kind of like whether you're talking about the very like local curvature of the model, or you're talking about making a very big step of like completely erasing the information. One good thing about gradient-based methods with respect to perturbation-based methods or erasure-based methods is perturbation-based methods. They basically require you to run the whole model every time you make a perturbation. So if you're running Lime with like 100 different perturbations, that means you need to run the model 100 times. Whereas for gradient-based methods, you only need to run the forward algorithm once and the backward algorithm once. And so because of that, gradient-based methods can be much more efficient. And so very often, another thing that people do is you run a gradient-based method first to identify the important looking words, and then you apply a perturbation to the words that look most important and just rule out all of the others. Any questions here? Okay. So another explanation technique is attention. And so attention, like as we know, is a very important part of many different models. We can use it to interpret things like entailment or image captioning, document classification, etc. There's also really nice tools like BERTviz that allow you to like look at the attentions on the internal of your favorite models. So this is it's definitely a good tool. However, attention actually, as I mentioned before, for these techniques here, these gradient-based techniques, there's kind of an intuitive explanation, which is like, if I take a very small step, how much is this going to affect the prediction? For attention, there's no intuitive explanation about how we really can't say anything about how we would expect a particular input to affect the model based on the fact that it has a high attention or low attention value. And in fact, there is a series of papers that basically say the first of the series of papers was saying basically we can use attention to interpret models. Then there was a famous paper called Attention is Not Explanation, which basically shows that there's no guarantee that attention would allow you to interpret models. Then there's another paper called Attention is Not Explanation that basically says, oh, but in actual cases, it is the case that attention is pretty good for interpretation. And so I personally, like my personality, I like clean things. I like explainable things. So intuitively, I like gradient-based explanations and erasure-based explanations better. Or perturbation-based explanations better, but we actually have a paper where we called Evaluating Explanations, How Much Do Explanations from the Teacher Aid Students? And basically what we did here was we had a teacher model that we were trying to basically explain, and a student model that we were trying to learn, with the idea being that if we have very good explanations, the student model should be able to mimic the teacher model with very few training examples. And just to give an intuitive idea, what if I told you this entailment model will classify everything that has a negative word in it as contradiction? Just to give an example that from the one that I put on the slide here before, on the white blackboard here before. If I told you that as a human, then you should be able, without even looking at any examples at all, be able to like mimic this model and understand when it's going to work, when it's going to fail. And so the idea is like, at least for humans, you know, if we give a really good explanation, they quote unquote understand very quickly and would be able to simulate the model's performance. And we basically do the same thing where we have a teacher model. We teach a student model with either just demonstrations of the teacher model's performance, or we teach the student model with demonstrations of the teacher model's performance and explanations. And so I like this paper a lot because it gives you kind of like a formal framework to evaluate whether explanation is working or not. But importantly, we also evaluated a whole bunch of explanation methods, including the gradient-based methods, the ones that I talked about before. And the funny thing is, attention like won every time. So I don't like the idea of attention as an explanation method because, you know, it's like less clean. It doesn't make as much sense as these gradient-based methods. But after I saw these results, I kind of had to like give in and say, well, maybe attention is like good. You know, maybe we should be paying attention to it. That was an unintentional pun, and I hesitated before saying it, but I said it anyway. So yeah, anyway, that's a piece of evidence that attention may be a good explanation method after. Yeah.
Given the paper with the title "Attention is not,"
yeah,
clearly there's another paper we need that is not
explanation. Yeah. Infinite recursion is an important part of language. Yeah.
So there be a caveat to these results where maybe attention, like different explanation methods are useful for a model form, but maybe not for people. So it might not make as much sense to a person looking at the attention output of the model, even if it has like the most information in that model to learn.
Yeah, so that's a really good point. And just to repeat it, couldn't there be a caveat to the results that it might be easier for a model to learn from a particular type of explanation than for a human to learn? And yeah, I definitely agree with that. Actually, one of the reasons why we proposed that framework was because previously people had done research where they tried to get humans to learn from explanations, and it turns out humans weren't able to learn from any explanations very well. It's not because humans aren't smarter than the models. It's rather that the humans didn't have the patience to look at 500 examples. And you needed 500 examples to learn, like in our models as well. So that being said, I've looked at the outputs, and I think, so we have two pieces of evidence. There's also, I don't want to talk only about my papers, but I kind of like them, so I'm going to do it anyway. So we have another paper that we just wrote. This paper, and basically what we do here is we optimize the explanation method to do well at this kind of like teacher-student task. Like we learn explanations that are particularly good for learning models from. And we have two pieces of evidence that these might also be good for human learning. They're not like decisive pieces of evidence, but they're pretty close. One is that like these are the learned examples, and you kind of can look at them and they look pretty intuitive, like pretty intuitively good. They're focusing like specifically on the words that we think should be important. Also, we have some other examples from image classification that show that. But another important thing is we did experiments on plausibility, where plausibility is like annotated by humans, where like they basically ask humans, what do you think is the most important words to be like, what are the most important words to make a decision in this corpus? It's a really bad idea to evaluate models only on plausibility, because plausibility isn't telling you anything about whether that's what the model actually used, right? Like, so for example, in the example that I showed with like atheist versus Christian before, like using .edu is what the model was doing, but it definitely, like, humans might not mark that as the most plausible thing. They might mark that as something else. But anyway, if there's higher overlap for something with respect to plausibility, at least it shows you're getting closer to what the human said was important. And in this case, like the learned models here also did that. So I think there's probably some correlation. Yeah, it's a very, very good question, though, and you can look more at this this paper coming out soon in Neurons. Cool. Any other questions? Okay. So next, I'd like to talk a little bit about model probing. In model probing, basically, there's a couple ways you can do model probing. And we talked early in the class about like sentence encoders and word encoders, and you can do probing of both. In the sentence encoder, basically you take the sentence embedding and you try to probe it for some variety of information, like the tense of the sentence. And in like a token probe, you would do a probe over the token representations. You might try to figure out what like part of speech it is or something else like this. There's a more general framework called edge probing. And basically what this allows you to do is it allows you to probe for many, many different varieties of information. With the reason being that most varieties of like linguistic information can be represented either as a label on a span or a edge between two spans. So this could include things like parts of speech, because the parts of speech are like a label on an individual word. It could be about entities, because that's a label on a span, or it could be about like syntactic dependency edges between words, because those are like edges between spans. So there's also a toolkit called Giant that was created to make this kind of probing easier that you might consider. The code is a little bit old, so I don't know if you necessarily want to use this or not, but you could take a look at it. So yeah, sorry, basically the idea is you train a probe and then you measure its accuracy, and that gives you an idea of how good the model is at capturing certain varieties of information. However, there's a few issues with probing. The first issue is you don't know necessarily whether you're interpreting the representation or whether the probing classifier essentially was able to learn the task itself without even, learning anything interesting in the representation. So one example is like, let's say we were training a part of speech tagger to figure out whether word embeddings captured part of speech. Another thing that you could do is you could just completely randomly assign labels, and a strong enough probe would still be able to memorize these labels and do very well at the task of part of speech tagging, because it would just remember, like, you randomly assign the word the to like X, and the word a to Y, and the word it to Z. And so basically, like, let's say you had a probe that consisted of a multi-layer perceptron, it wouldn't have to know any information of part of speech. It could just learn the mapping from like the input to the output, no matter how complex this was. So one way to solve this is to use something called information theoretic probing. And basically the idea is that if you're able to learn this more efficiently, or with fewer data points, then it's more likely to be like a real effect that's appearing in the embeddings, as opposed to a like arbitrary thing where you just learn the mapping between the input and the output. And there's a couple of ways you could do this. One way you could do this is by basically training the model on progressively more data points and observe the area under the learning curve. And the area under the learning curve is essentially like, if it's higher, then the probe is probably more successful. Another issue is that when you're probing, you can only probe for properties that you have supervision for, or that you know a priori. So you can't necessarily, like, let's say there's some really interesting phenomenon that was caught in the, captured in the embeddings. Probing would not find that for you, because if you're only probing for part of speech, you can only say something about part of speech. Another thing is correlation doesn't necessarily imply causation. So it's not necessarily the case that the fact that you're doing well at the probe indicates that the information is necessarily captured in the embeddings. It might be some other, like some other type of information that more directly implies the thing that you're probing for. Okay, so yeah, that's all I have for today. One thing is, one final comment, I guess, is interpretation is really interesting, but it's really hard. If you're interested in interpretation, I think one of the biggest problems is like thinking about what you want to use it for at the moment. Like, why do you want to interpret your model? And very often the interpretation techniques we have are like divorced from like what we want to do with them. So I think filling that gap is still like a big issue in interpretability research, and I'm interested in it. So I'm happy to talk about it. Okay. Any questions, discussion, anything like that? Yeah. Oh, what's the argument against attention being used as an explanation? I mean, basically, let me give a counterexample. And we also actually have a paper where we demonstrate that you can arbitrarily train a model to not focus on any of the words that you think are important, but it still does a very good job at classification. But just to give a counterexample, like let's say we're talking about attention in our first layer of our model. And we have an attention value of 0.5, 0.2, 0.2, 0.1. So this looks like the most important value here, right? Let's say we arbitrarily modified this word embedding by 1,000, or multiplied the word embedding by 1,000. Now we can get essentially an identical effect with something that looks a lot more like that. I mean, obviously you need to make that add to exactly 1, but you could get something like this. So just by modifying the input, you can change attention arbitrarily and still get the same effect. So there's no guarantee that attention will be good for exploration. However, in organically trained models, it is the case that it seems to be good much of the time. So, yeah. So is the trend right now to treat explanation as a feature extraction technique so we can increase the accuracy? Yeah. Yeah. Well, no, so just to clarify, like I talked a little bit about our work on how we could use explanation to train downstream student models. That's more just as a way to evaluate whether our explanations are actually telling us something, as opposed to the final goal of explanation. The final goal of explanation, I think, is like what I talked about before, which is like trust, understanding, like basically increasing trust, identifying problems with the model where it's fitting things that it shouldn't be, so you can improve the model accuracy, identifying biases, other things like that. So I think that is more or less unchanged. Yeah. Yeah. So when we talk about trust, whose trust are we talking about? I think it could be for the model developer. It could be for the person you ship the model to. It could be for the person who's using the model. So yeah, it could be any of them. Another thing is it could be for people who are using the model downstream in like a human machine learning setup. However, there's an interesting counterintuitive result. Let me see if I can find this. Called understanding the effect of accuracy on trust in machine learning models, I think. No, actually, sorry, no, that's not it. But I'm pretty sure it's a paper by Hannah Wallish, who is also the author of that paper. Yeah, okay, maybe this is the paper that I was talking about. But anyway, basically what they show in the paper that I'm thinking about, I think it's this one, is they demonstrate that trust in the model is not necessarily correlated well with how well the model can be used in a like human machine like learning setup. So like, in fact, people might trust it more, but they're not any better at like actually using it in like a human machine collaborative setup. So I have another question. Why is probing considered as an explanation method of NL models? It looks more like a quality assessment of the word embedding. Yeah, it basically is a quality assessment of the word embedding, but it's a quality assessment with respect to individual characteristics that you're interested in. So because of that, it kind of tells you a little bit more. You could almost view it as like interpretable evaluation of like word embedding, like models maybe. And then the final question that I'll take is, how do techniques like influence functions that find the most influential training examples fit in the overall framework of model debugging? They could just be data set artifacts, but what can we learn about the model when the prediction is wrong and the most influential instances are not artifacts? So yeah, I didn't cover influence functions. It's a very interesting like alternative approach. Basically what it does is it identifies the input examples that had the largest effect on the model itself. And I don't know if I'm going to have enough time to talk about it in 0 minutes, but basically, it's another tool in your toolbox. It's particularly good for identifying problems in data. And the way it works is it basically finds the data points that had the largest influence on in changing the prediction on an individual example. So it could fit in here. It has kind of a different effect, I guess. So, yeah, okay, thank you, everyone. I can take any other questions.